Good afternoon, and welcome to our September installment of our webinar series. I'm Jackie Baxley, and I'm joined today by my colleague Jake Smith, and we are going to walk you through an emerging hazard in the workplace, specifically as it relates to the EV manufacturing place. So just to start with a few little administrative notes as we get started here. All of our attendees are in listen only mode. If you have a question, you should be able to see through the webinar platform. You can either use the chat function to send us a question, or you can use the question and answer to send us a question. Those of you that are not listening to us live but are catching this recording, at the end of the presentation, you will have both mine and Jake's contact information. So feel free to reach out to us directly if you have a question and you're listening to this through a recording as opposed to live. So with those little preliminary details out of the way, let's go ahead and hop right in. So HRP is bringing this webinar topic to you through our webinar series. We try to do about 6 or so technical webinars a year, in addition to our online training that we offer, as well as in addition to our in-person training that we offer. And HRP, for over 40 years, we have worked with our clients to assure that they move their environment forward. And what we mean by this is we work to minimize the environmental and compliance risk associated with our clients' projects and help them reach their business goals. We are a multidisciplinary environmental compliance and engineering consulting firm with several offices across across the country. And then this topic that we're bringing to you today fits into our environmental health and safety and sustainability practice area, and specifically where we help our clients with health and safety compliance as well as industrial hygiene concerns. And my colleague Jake is going to be leading us through the majority of this topic today. Jake is a principal and senior project manager with HRP with over 19 years of experience in environmental health and safety consulting. He has a vast understanding of environmental health and safety regulations such as OSHA, EPA, and state regulations, as well as a number of consensus standards such as NFPA, ANSI, and ASTM. As well as the health-based exposure guidelines that we'll actually be talking about a little bit today. You'll hear the acronyms ACGIH, NIOSH, OSHA, and as an industrial hygienist, his primary service focus on industrial hygiene and occupational exposure strategies, community exposure, development and implementation of safety plans and procedures, and qualitative and quantitative exposure assessments. So he's going to be bringing that expertise to us today as we talk about this emerging hazard that we are seeing in the EV manufacturing space. My name is Jackie Baxley, and I work closely with Jake. I am also a principal here at HRP, and I lead our environmental health and safety and sustainability practice. I hold a professional engineering certificate in several states and have over 25 years of experience as an environmental engineering and risk management consultant, specializing in the areas of compliance, sustainability, and management systems. So a little bit about the topic that we are going to be presenting on today. There's been plenty of talk about hazards associated with batteries in the EV manufacturing and supply chain, and rightfully so because of the hazards associated with those batteries. But there has been less information about another associated hazard, and that is the hazard of the magnetic fields from components that are associated with EV manufacturing. So what we're going to cover today is an overview of magnets and these magnetic fields, and what are the potential health effects and exposure limits associated with these magnetic fields. Once we have understanding of the fields and the exposure concerns, then we're going to talk about how to reduce those exposures and other measures and considerations for safety programs. And then we'll just wrap up with some other consideration relative to these magnetic components that we widely see in the industry. Here in just a minute, I'm going to hand it over to my colleague Jake to lead us through. Once Jake starts talking, I am going to upload to the chat two handouts. So you will have the following handouts available to you. One is going to be an acronyms list as well as some helpful links, and the other is going to be a PDF of the presentation. So you will get a copy of the presentation. So with that being said, Jake, I will hand it over to you.
Hey, good afternoon, everybody. As Jackie mentioned, it seems there's been a lot of EHS focus with electrical vehicle manufacturing, especially that of batteries, both in the manufacturing side with chemicals and some of those systems, and then also on the assembly side where we're worried about fires and handling and that kind of thing. But then one other area, that we've kind of gotten into and spent some time is the unique electrical hazards. So all that's kind of related. There's some good standards, some good references out there. But one area in EV manufacturing, as Jackie indicated, that started to gain attention is potential hazards present by magnets and magnetic components. So we wanted to provide some general information on the increased use of magnets in the industry. That's definitely something that's occurring. Some of the associated hazards and assessment methods. So that's a lot of what we do and where we've been spending our time. And then just a general view of controls that can help mitigate some of those hazards. So as we move into the presentation, we'll just kind of start with going over some of the basic hazards and taking a step back and looking at general categories of hazards and kind of all that comes together from an occupational exposure perspective. So on the first slide, what we're really focusing on is for occupational exposure hazards, they typically fall into one of four categories. So we've got our physical hazards, which we're probably all fairly familiar with, things like noise, vibration, elevated temperature, cold temperature, those kinds of things, radiation. We've got chemical hazards, so that's pretty typical in an industrial setting and manufacturing processes. So we've got exposure to chemicals through the typical inhalation, ingestion, and then skin and eye contact. Biological, so bacteria, viruses, parasites, biotoxins, things like Legionella, bloodborne pathogens, those kinds of exposures. And then really ergonomics, which, most facilities have gained a lot of understanding in ergonomics and really ironed out a lot of that stuff, but definitely still a concern. But for the discussion today, we're going to be focused on the physical hazard category because magnetic fields are actually a form of non-ionizing radiation. So they fall into that physical hazard category. And we'll get into some of the specifics on radiation and non-ionizing versus ionizing and kind of what it means from an exposure perspective. So first, let's talk a little bit about magnets in general. I think everybody on the call has probably at some point or another handled magnets, whether it's a fridge magnet, whether it's something that you used in school or played around with for whatever reason. In simple terms, it's a material that produces a magnetic field and attracts certain metals and other magnetic fields. So magnets have two poles, a north and a south, and like poles between magnets. So if you've ever handled magnets or had two, and you tried to put the north end of each together, obviously that they repel each other, same with south to south connections, whereas opposite poles between materials north and south attract. So depending on the orientations of magnets really dictates how the poles work and how the magnetic fields and things overlap. So the magnetic field then, what results from the magnets, it's the region around the magnet where its force can be felt and is generated by the motion of electrons within the material. And we'll talk a little bit more about magnetic fields on the next slide. So again, the magnetic field, it's a form of non-ionizing radiation. It falls into a similar category of radiation that includes things like radio waves, microwaves, infrared radiation, and visible light. I think a lot of us have probably heard some of that terminology. And in general, non-ionizing radiation occurs at lower energy than ionizing radiation, and it cannot remove electrons from atoms. But this form of radiation can still generate heat and of tissues and other cellular effects. And we'll get into some of those details and how they specifically relate to magnetic fields. So for all of us that are on Earth and have spent some time on Earth, we're exposed to magnetic fields on a daily basis. The Earth actually has a natural magnetic field that ranges from 0.03 millitesla to 0.06 millitesla. And the field serves to provide shielding from solar winds and cosmic radiation. So if you look over in this little illustration on the right side of the slide, You can see the Earth and the North and South poles. You can see how the magnetic field and transfer of electrons occurs from North to South poles, and then kind of how that interacts with the atmosphere and things like that. So the concept's going to be very similar to what we're talking about in the industrial setting because magnets operate in a similar fashion. So we'll have some more slides that are specific to the types of magnets that we would see present in the workplace, but this gives you kind of a general idea of how the magnetism works overall. So magnets and magnetic fields in industry. So similar to properties of naturally occurring magnets and magnetic fields, magnetic components have been gaining popularity in manufacturing and industrial applications. So the places where we're seeing most of the attention is likely falling under that electrical vehicle manufacturing category. But some of the areas where they've been used in a long time, but they're kind of changing the properties of magnets and how they use them. So DC powertrain manufacturers, they've had these kinds of hazards and concerns present for a long time. So medical imaging, if anyone's had an MRI or certain types of other imaging, they rely on magnetic sources. Aluminum smelters and manufacturers, and then aerospace. So all of these industries, and there's plenty more that are using these. Electrical vehicle manufacturing, though, is one where it's gaining popularity, and we're seeing kind of most of the conversion to a lot of the automotive components and parts where we didn't have these before. We're starting to see them and getting more information from suppliers on specifications and things like that, just to better understand kind of their role and how they're used in these auto parts. So why the increase in reliance on magnets? After doing some research, we're finding that it's likely mostly attributed to the compact size. So you can get a lot of energy in a small, lightweight design. Durability, depending on the type of materials that are used in the magnet, the corrosion resistance and reliability in harsh conditions, the cost, there is definitely a cost benefit to go into this form of energy and how they're used in the automotive space. And then temperature efficiency. So certain types of magnet materials maintain their properties under extreme heat. So, you'll have rotating automotive parts or something where we've got high wear components and things. Moving to magnetic type installations really kind of increases the efficiency overall. If we're going to go to the next slide, we'll get into some more of the properties. So what are the components? Where are we seeing the electrical vehicles and in manufacturing? So electric motors, there's been for a long time now, we've had batteries or we've had magnetic components in electric motors. They're just kind of shifting how they're used in the placement of some of those magnets. Alternators, sensors, power accessories, transmission systems, fuel pumps, audio systems, and chip collectors. And I don't know how many, folks on the call have worked on cars or been around automotive type stuff in the past, but some of these have had magnets for a long time. So audio systems, for anyone's had the old Sherwin Vega speakers at their house or things like that, those have always had large magnet components to them. Chip collectors would be things that are typically in like an oil pan or a hydraulic oil reservoir that's made to collect some of the machining chips and stuff. If you've ever taken out, changed your oil, stuff like that, a lot of times the bolt will have an actual magnet on it just to collect those chips and stuff. So some of these we've seen and some of these we anticipate, but some of the other components like the transmission systems and some of the alternator, the way that they're doing them now and some of the sensors, those are kind of unique and it's really important to kind of evaluate some of those. And we'll go into some of the precautions and thought process on the front end of it just so we can better anticipate because when we talk about magnets and magnetic fields, one of the big concerns is really where does the field land in orientation to the person who's going to be handling the part or component. So if you picture these flowing through a manufacturing process, they're going to be handled in several different capacities. Some are going to be elevated, some are going to be sitting on a conveyor, some are going to be on a bench, and those kinds of things. And like, for the maintenance side, when someone's doing testing or inspections and that, all of the orientations are going to be different. So that magnetic field, while it stays constant from the part, it's actually moving because of the way that we're handling these components through the manufacturing process. So we'll talk about that again in more detail as well. So how do magnets result in occupational exposures? So the basis of exposure is on the strength of the magnetic flux density, which is basically the magnetic field associated with the component. So this is typically expressed in units Tesla or Gauss. And then two primary forms of magnetic fields. So the first one, which is the topic that we're primarily discussing, is on static magnetic fields. So those are magnetic forces that do not change in strength or direction over time. So some examples would be Earth magnetic fields and permanent magnets, versus alternating magnet fields, which typically have some type of an energy source associated with them. So those are fields with strength and direction constantly changing depending on the electromagnetic waves. So some examples would be transformers, power lines, motors, and those kinds of considerations. So it's important to understand, though, that there are two forms, because from an assessment perspective and a controls perspective, we're talking about two different types of assessments and two different types of controls. So one thing that's unique to magnets is you really have to kind of understand what you're dealing with in order to evaluate and assign controls to help reduce exposures. So here's illustrations of just some kind of general static magnet components and their properties. So on the left side, we've got a magnetic field that's associated with a bar magnet. So you can see the illustration showing the North Pole and the South Pole, and then the travel of electrons through the space, which is what's generating that magnetic field. And then over on the right side, you can see the orientation of the attraction, and then how they no longer attract depending on the orientation of the magnet. So there on the top right, you're showing North Pole to North Pole, and you can see that they push away. And then if you look at the bottom right, you can see the North Pole to South Pole, and then you can see that magnetic field that's actually generated between the two of them. So when we talk about magnetic strength, which is kind of the basis of the assessments and controls that we're doing, we're talking about the field strength in the areas which are the greatest density of magnetic field lines. So that's where we would expect to see the highest values. And again, those units would be in Tesla or Gauss. So that's what we're looking for when we're doing the assessments, is we're not just taking a single measurement or making a determination off that. We're having to actually trace the magnetic fields to figure out where it's strongest, where it's weakest, so we can come up with some of our thresholds. So we're going to move into some discussion on potential health effects, and then also get into some conversations on exposure limits, because that's kind of what's going to drive the precautions and controls and stuff like that. So we'll get into those in the next series of slides. So one of the challenges with this form of non-ionizing radiation, and this actually goes along with some of the other forms of non-ionizing radiation, is there's currently limited research on high-frequency exposure hazards or long-term exposure hazards. There's limited evidence of biologically harmful effects or exposures even up to several Tesla, which is pretty high numbers. And then some concern associated with blood flow in and around the heart and other major blood vessels, but overall results are unclear. And in researching this, one of the challenges that I found is that a lot of the studies where they give statistics or where they try and evaluate for effects and stuff like that is usually it involves workers that are exposed to a wide variety of other potentially harmful agents, and they're not able to differentiate whether it's an exposure that's straight from, this type of non-ionizing radiation, or is it the chemical XYZ, or is it the elevated temperatures, or all those kinds of things that may be exposed to on a normal basis. But overall, we'll get into some of the information that we do know, which is, the important aspect of it, and really what the controls and stuff should be based on. So what we do know is there's currently more focus on the short-term concerns related to things like eye-hand coordination, visual contrast sensitivity, and other sensory effects such as vertigo, nausea, and changes in taste. It seems like nausea and dizziness seem to be the most common, especially in the types of exposures that may be relevant in an industrial setting where maybe we're not dealing with, research type, extremely high value magnets and things like that, but they're more components and stuff where there's localized magnetic fields and things. But that really seems to be the most common, would be more on the nausea and those kinds of interactions. A major concern, and most important probably with what we've been doing, is looking at the impact that a magnetic field can have on medical devices and medical implants, even at low field strengths. So if anyone has ever been or ever had to have an MRI or something similar done, you understand the lengthy questionnaire that you get, asking questions about, metal shavings, piercings, any of that kind of stuff, pacemakers, any kind of those sensitive medical devices. That's really where the biggest concern is, in an industrial space, only because, it's hard to tell where these fields start and stop without doing these assessments. And you have an aging workforce, or you've got a variety of employees that may have medical conditions or implants or things like that. And that's probably where the biggest area of attention is on this, on this kind of hazard, is really trying to understand that side of it, because those are low values, and it really doesn't take a whole lot to where it can disturb some of those medical devices. And then lastly, we've got crunch and pinch hazards. So depending on the magnetic pull of the device, and really where is the device in relationship to, where we may have components, parts, tools, other parts that, or other things that we're using in the manufacturing process, we've got to worry about those crunch and pinch hazards, because as we're handling these components that may have magnets in them, it's going to depend on where they're placed and how they're moved across the space and things, in the production process. So what are the regulations and guidelines that we have to talk about these? So OSHA does have a section, for extremely low frequency radiation. They refer to it as ELF. The challenge is that there's no current OSHA exposure limits, but it does reference ACGIH and then also ICNIRP as guidelines that can help with establishing programs and evaluating occupational exposures. So we're going to talk about those in a little bit more detail. But the American Conference of Governmental Industrial Hygienists, ACGIH, they do provide threshold limit values for static magnetic fields. And the way that they break them up is really whole body, limbs, and medical device wearers. So again, it comes back to how the orientation of the parts or components are going to be used in the environment to determining which TOVs apply and how to use them. And then the same respect, the International Commission on Non-Ionizing Radiation Protection, the ICNIRP, they have similar limits. It's just categorized as head and trunk and limbs, and incorporate a limit for general population, which is not something that is provided by ACGIH. And for those that don't know, I mean, both of those standards, or both of those set of guidelines, ACGH and ICNIRP, are widely accepted in the United States, depending on what the application is. So typically where OSHA doesn't have a limit, which would be a regulatory limit, we start looking for, other industry guidelines that we can pull in. And ACGH is very popular from an exposure perspective, especially for chemical and biological exposures. And then again, the ICNIRP, the FCC and other organizations rely on them to help with guidelines related to non-ionizing radiation. So that's why we typically use them in the assessments and kind of assignment of controls and response measures. So in a little bit more detail, so ACGIH, so static magnetic fields. So their whole body limit for general workplace is 2 Tesla. And then the whole body for special workplace training and controls is 8 Tesla. And really the big difference between when they say 2 Tesla or 8 Tesla comes down to how the workspace is set up, and how much or how familiar the employee may be in the space and with what they're doing and some of the hazards. So one of the big ones, the difference between the 2 and 8 Tesla, are projectiles. Really, you need to have a controlled space or a controlled environment where you're using these magnets and magnetic components once you get into field values of greater than 2 Tesla. Less than 2 Tesla, as you see when we get down to the bottom, we've got the medical device wearer limit. So that's 0.5 millitesla. That's a pretty low number. So it's important to keep in mind that, while the average employee may be able to be exposed up to 2 Tesla, we've got to have a good way to identify sensitivity for medical device wearers and those with potentially medical implants that could be attracted by magnets and magnetic fields. So those are pretty much the concerns with ACGH. And then I mentioned previously too that there's a second form of electromagnetic energy, which would be things that are charged or that are provided with a power source. So there's other standards that apply to those. So it's important to remember to apply the right limits to the right type of exposure. So that's something that, we typically monitor to try and figure out what type of exposure it would be and then apply the correct exposure limits. And then, as previously mentioned, the IC and IRP, they've got their standard magnetic field limits as well. So they have an exposure of head and trunk of 2 Tesla, and then similarly up to 8 Tesla under controls and training as specified by ACGH. They have an exposure limit for limbs, so 8 Tesla. And then they also provide a general public, which is 400 millitesla. And I thought that value was kind of unique because if you look at the medical device wear limit of 0.5, you think from a general public perspective, some of that may have overlapped, but in reading some of the literature behind their standards, they're more oriented to the industrial and to the biological type events more so than the medical device side of things, but they also wanted to provide a limit. So what they did is they just took a safety factor, I believe of 5, and then just applied it to the exposure of head and trunk, the 2 Tesla, and that's where they got their general public number. So it's important to remember, though, that there is still a lower limit for medical device wear or those with medical implants. So what are some exposure reduction measures and considerations? We'll talk a little bit about that. So we've got kind of a general background on magnets and magnetic fields. I know we went through it pretty quick and pretty high level, but it's pretty straightforward stuff as long as we understand the type of devices we're working with. We talked a little bit about the hazards, mostly being the medical device wearers and the implants and things like that. And then now we're going to move into just some of the exposure reduction measures and considerations. So controlling occupational exposures, we recommend a multi-step approach for controlling exposure to static magnetic fields. First one, and probably something I find most important, is the data collection and review. We'll talk on the back end of this a little bit about ways that we can implement this and stay ahead of it. But at the same time, when we get new components and new parts and things like that, we're finding the availability of information associated with those parts to be pretty descriptive as far as the types of magnets, the power of the magnets, the anticipated magnetic fields. We're finding that information to be available. And then what's also helpful too is getting actual cut sheets or schematics of what the parts will look like and kind of where the placement of the magnets will be. Because if you remember the magnetic fields and some of those illustrations, they do drop off pretty quickly from the actual magnet. So if you have a magnet that's buried inside of a part that's 12 inches wide, you may not get much of a reading by the time you get to the perimeter of that part or component. Whereas if you've got, a small diameter part, or if you've got stacks of magnets that are located on the outside, that magnetic field may extend, 8 inches or 10 inches or even 15 inches from that magnetic source. And that's where you need to worry about it, because now we're talking about potential interferences with employees and exposure potentials. So the other element, field assessments and exposure determination. So we do know, if we do know that we're getting magnets in, we know that we're putting in a new process line or bringing in a new part. We want to make sure that we're looking at what those field strength values would be for the areas where the employees will be occupying them. And then we'll talk a little bit about how those assessments are performed. But it's really kind of like any hazard. It's just kind of measuring what the values are, applying the exposure limits, and then looking at controls for how we reduce them or seeing if they're acceptable. For the controls, like anything, we want to follow our hierarchy of controls for our exposure reduction and control measures. And then the last piece, which is probably as important as the others, is really the ongoing monitoring. And that's where, we've got the values where we want them. We're sure everybody's safe. We're following all of our procedures. How do we make sure that stays in place and as a check and balance? So we'll talk a little bit about each one of these individually. So data collection and review. So as I mentioned already, so manufacturer supplier specifications associated with the magnetic component, the type and quantity of magnets in the component, and the anticipated magnetic field strength. As important are definitely the diagrams or similar to the parter component, because we really need to understand where that magnet's going to be oriented within the part, and how the part will have to be, how the human will have to interact with the part. So where they're going to be placing it. Is it going to be on a table? Is it something where we have a lift assist and it could potentially be at their chest height? All those kinds of things. We really just have to understand how the part works and where the placement of the magnets in the parts are. And then really an assessment on how the part or component will be handled throughout operations at the site. So it's not as simple as just looking at, okay, we know that the box is going to go over here and the magnet's going to be put on the table, and now we need to worry about what the magnet is on the table. We really need to think about from kind of start to finish on how the workflow works throughout the manufacturing facility with that magnetic part or component. So things like shipping and receiving, material handling, assembly, maintenance, product testing, and even on the recycling and disposal side, depending on what the device is and how it's being handled. Those are all things that need to be considered. For field assessment and exposure determination, so if we know we're getting some type of a magnetic component in, it's a good idea, even if we get the manufacturer specifications, it's a good idea to go ahead and take some field measurements just for confirmation, just to make sure that the part that arrived is actually the same part that we have the cut sheet for, or the specification for. So field measurements are typically collected using a magnetometer or a Gauss meter with a measurement probe. It's a little unique for magnets because a lot of these meters come in specific ranges, and it's important to make sure that you're using the right type of equipment, for the right type of magnetic field. So whether it's whether it's a static field or whether it's an alternating field, and then also making sure that the range of the probe matches the magnetic field that you're looking for. So sometimes it's handy to have a couple of different probes where you can be sure that you're capturing all the magnetic field in the device you're using. Very similar to an electrical meter, an ohm meter that you use for doing electrical work. Measurements are recorded first by measuring ambient natural occurring background magnetic field strength. So if you remember, I did mention that that the Earth has a naturally occurring magnetic field, but at the same time in a manufacturing setting, you're going to have lights, you're going to have electrical installations, you're going to have a lot of things nearby that are also generating electromagnetic fields that are going to get picked up by the meter. So it's important that you understand what the background levels are so that you can figure out, what's actually being contributed by the part or component, or what's being, contributed by things that are naturally occurring or other installations that are in the general vicinity. So we usually start just kind of back up as far as you can and figure out where your baseline numbers are, and then just keep working towards a magnetic source to start picking up where the fields start and stop. And then you continue working towards a magnetic source at small increments. And really what's important is establishing that medical device wearer limit to try and figure out what that is. And for anybody that's done this or used real-time meters with gas detection or anything similar, you'll notice there's a lot of variation in how you're holding the meter, how you're handling the meter, the orientation of the part or things that we're measuring. So taking a lot of measurements is important, and then also changing the orientation of the measurement devices is important to make sure that you're accounting for the actual transfer and the layout of the magnetic field as you're taking the measurements. And then the other thing too is looking at the other thresholds. Once you know where your device wear limit is, working towards to make sure that, we're not going to exceed a PEL for limbs or anything like that. Okay, so exposure controls and exposure reduction measures. So we know that we've got magnetic components. We've done our measurements and things, and we're seeing some elevated values, things that we're not comfortable with. What do we do as next steps? And we'll talk a little bit about that. So some of the reduction measures that we have, we've got passive and active shielding. So depending on the type of magnetic field and the type of part, sometimes this is possible, sometimes it's not possible. Sometimes the part casing itself, so you may have a magnet that's embedded in an automotive part, and the material used in the casing of the part may actually provide some shielding. But those are all things that have to be evaluated and looked at with the manufacturer and their specifications and taken field confirmation measurements. But there are different types of materials from a passive perspective. And then active shielding would be creating an additional magnetic field that cancels the other one out. So those are both options. I would say passive is probably more common than active shielding. But again, in the manufacturing setting, some of these next steps that we're going to talk about are probably going to be more applicable, just because of the way that the manufacturing has to happen and how parts are handled and how they have to workflow through a production process. So the next and kind of to that attention is increasing distance between the employee and the magnetic source. So a lot of times the magnets that are coming in these components, the magnetic field drops off pretty quick. So a lot of the exposure happens within the first, call it 6 to 12 inches. And that's not a hard and fast rule. I mean, you could get larger magnets or different types of materials that maybe that magnetic field extends beyond that. But for some of the assessments we've done and some of the research we've done, it seems like, that really in that first 6 to 12 inches where you're going to have a lot of those thresholds. As you approach the magnet, obviously those values go up, and as you distance yourself from the magnet, as long as there's not another magnetic source, the distance drops off. So increasing the distance between the employee and the magnetic source is very important. Next is reducing tools and components susceptible to magnetic attraction from areas with elevated magnetic fields. So we usually recommend this, once you hit that 5 millitest, the first threshold, the medical device threshold, we usually recommend this is where you start looking at to see if there's potential for tools and other components that can be in the workspace that would act as projectiles, or even the part itself coming loose and pulling towards another device when maybe you're not holding it tight or something, and obviously could cause some injuries from a crush pinch perspective. And we'll talk about that a little bit more as well. Because there's some other things too with like clothing and some of the stuff that you're doing that could interact with the magnetic fields. Another is controlling access to areas where elevated magnetic fields are present. Obviously, there's HR concerns and HR policies and things like that around medical screening and work tasks involving limitations and stuff. But at the same time, it's important to find ways to control access to areas where we know we're going to have elevated magnetic fields, especially for those that are susceptible to some of those lower frequency magnetic fields that may have medical devices or implants or things that are prone to or elevated when they're exposed in those environments. And then lastly is signage and training to inform employees of the potential hazards where elevated magnetic fields may be present, or where there's a concern for medical device wearers and those with medical implants. And sometimes this can get a little tricky because, as I mentioned, a lot of times the hazard's pretty close to the part or component that's generating the magnetic field. So it's important to try and figure out, where do you start and stop restricting access to these areas? Is it right up to the part and we can maybe keep it in the corner of a work cell, or is it the whole work cell? And then also as that magnet or magnetic component travels through the manufacturing environment, understanding that there's likely going to be some hazards and things that follow the magnet along. So we've got to also consider the other workstations and the conveyance through the facility. Okay, next slide. Okay, so the ongoing monitoring perspective. So we've put in our controls. We've got everything where we want it. Everybody's been trained. We're feeling good about the scenario and how we have it set up now. So how do we keep this in place? What are our checks and balances? Just like any EHS program, we've got to have a way to keep it effective. So some ideas and suggestions would be implementing management of change and pre-startup safety review practices to ensure that new parts or components are evaluated prior to introduction into the workplace. So if you don't already have a facility management of change, we call it MOC just because we love our acronyms. But if you've got an MOC program or a pre-startup safety review program, it's important that you roll these types of process changes and modifications through those programs so that you can understand what the parts and components are coming in as. And one suggestion would be, if you know you're going to be in a scenario where you're getting parts or components that could have magnetic elements to them, you may have to actually update those MOC and PSSR programs, because a lot of the pre-populated data is kind of general in nature, and it may not prompt you to start looking for magnets or magnetic energy if you just rely on like templatized MOC and PSSR programs. So that's one recommendation, is just to make sure that we have MOC and PSSR in place, and if we're using those tools, that they would address this type of hazard and they would prompt the user to look and make sure that the parts wouldn't have these components in them, or if they do, taking the next steps to evaluate them and make sure that they're okay before we bring the process online. Next would be periodic field measurements to capture process changes or other considerations that may impact exposure levels. As I mentioned, a lot of it's determined by where the magnets are oriented in the part or component, and then where that part or component is going to be oriented throughout the manufacturing process. So it seems like, especially in the automotive space, we make a lot of changes. We make a lot of conveyance changes from how parts get from A to B and that kind of thing. So just making sure that we're doing periodic field measurements to make sure none of those boundaries have changed, or we don't need to make adjustments in where we're restricting access, or other kind of controls that we're putting in place. General workstation inspections and periodic audits. So a lot of times, just because we intend on a part to be handled a certain way or to be conveyed through a manufacturing process a certain way, doesn't mean that we're always going to do a good job keeping it going that same way or being handled the same way. So really doing some of those inspections and periodic audits, or finding another way to do that, is just another check and balance to make sure that things haven't changed, triggering us to where, okay, we need to step back and maybe do a management of change review to make sure that we haven't introduced new hazards or changed the hazards that we already have. And then lastly would be like a refresher training, and really trying to gain employee engagement, because one of the big things about magnets is you're not typically going to, for the fields that are going to be typical of a manufacturing environment, you're likely not going to know just by handling the part whether or not it has a magnetic field associated with it, unless you get some really strong magnets or really strong magnetic fields. But for the typical part or component, you're really not going to know that you're handling something magnetized unless all of a sudden your watch goes haywire, or you feel like your watch band or something's trying to stick to the part. Those kinds of things would be triggers. So it's important that employees are informed ahead of time that the parts and components that may have these magnetic fields, and some of the precautions and stuff associated with them. And then employee engagement wise, just, making sure that employees are participating in training, that they're participating in the workstation inspections and audits. They're taking care of where things are placed and signage and all that kind of stuff. So really just getting buy-in from employees on controlling these hazards is important. So lastly, we're just going to get into some other kind of general control factors. So what are some other control factors for magnets used in the workplace? So something that comes up a lot is jewelry and metallic related clothing items. So things that may act as projectiles, or pull an employee towards a part or component where we're not intending to do so. And maybe that in itself doesn't result in any kind of injury, but the fact of them being off balance, or maybe being pulled towards something, or their clothing could get caught and pull an employee into something much more hazardous than just a magnetic field. So obviously you'd want to limit jewelry and metallic components, which is pretty typical anyways, but it's just reinforcing it for these areas. Sensitive electronics, if somebody sets their new iPhone or something on one of these components, there could definitely be some issues. Or if there's any kind of troubleshooting and things, from if you've got somebody come in and programming a new machine or some kind of a robot or something, and they're trying to set their computer somewhere, just making sure that we've outlined where those boundaries are, and that they're familiar with, it could disturb electronics and things like that. Visitors and contractors who may not be aware of site hazards. So we always recommend having a contractor program to make sure that we're keeping them in the loop, and informing visitors and contractors on our site hazards. And lastly, something that's definitely worth considering is emergency response activities within an area of elevated magnetic fields. So if you've got some cells or areas where we have elevated fields, understanding where those are and what the values are, and then also the AED equipment or other resuscitation equipment that we have on site, making sure that we can still use it in those areas. And then if not, having a backup plan for if we have somebody that has a medical issue or medical emergency, then that area, what are we going to do if we can't use an AED or can't bring the AED in there? What's our backup plan going to be for that? So those are just some kind of other control factors and things to consider. And there's other stuff, but that's kind of the big ticket items. So with that, I'm going to turn it back over to Jackie, and Jackie's going to run through some stuff on the environmental side, just for a little bit of background in that respect.
Great. Thank you, Jake. I'll let you catch your breath before we start throwing questions your way. So yeah, just wanted to wrap up with just some other considerations. Appreciate Jake taking us through the health related concerns and exposure limits and control considerations, just to kind of wrap up with a few other considerations outside of the traditional health and safety space. First off, all associated with disposal. So, two things to take into consideration with disposal. A, how are we going to dispose it? And B, all of those magnetic fields and controls and potential hazards that Jake just walked us through, relative to, process manufacturing, those fields very likely are going to still exist in the waste handling as well. So waste from these types of components are typically going to be more like an off quality type situation. It's not like a something that we're using and because of its use, it's no longer fit for reuse and we're getting rid of it. It's normally going to be some type of your maybe off quality process. So just realize that manufacturing and process controls may need to be extended through the waste handling for worker protection. And then when it gets to the disposal, assuming that this isn't like a part or component that you can return to your vendor or your supply chain, if you are having to look at physically disposing of these magnetic components, magnets are not directly regulated by EPA, but they're kind of looped into the regulation, similar to how we see e-waste being looped into regulations and similar to how we see scrap metal being looped into regulations. And what I mean by that is typically with your e-waste and your scrap metals, if you are not recycling e-waste and scrap metals, then you have to be aware of, typically it's the metal components, how much of the metal components would leach should they make their way to a landfill, and it could end up being a regulated waste because of the metal components. However, if we recycle this material, then we kind of get to operate under those recycling regs as opposed to the hazardous waste regs. So with that in mind, magnetic components commonly contain rare earth materials that might not be recovered through conventional metal recycling means. So where if you've got these components and you're not able to return them to your supply chain for whatever reason, then likely what you are going to be doing is you're going to be engaging with your recycling vendors as to assure that you are following the proper protocols, maybe sending it to specialized recycling vendors to ensure that they are actually able to recover those rare earth minerals from those magnetic components. And then on the transportation side, whether it's waste, whether it's the actual finished part, whether it's just part of your value chain, please be aware that magnetized materials may be forbidden for air transit. So if those of you that are familiar with the transportation regulations, whether that's the Department of Transportation, which is what we follow here domestically, IMDG is the International Maritime Dangerous Goods. Those are the regulations that we follow when we are starting to ship materials over water through vessels and cargo containers and whatnot. And then IATA is the International Air Transit Association. Those are the regulations and protocols that come into play when we're shipping dangerous goods by air. So for magnetized material are forbidden via aircraft for any package which has a magnetized field of more than 0.00525 Gauss. And that's measured at that 4.5 meter area away from that package. As Jake was sharing with us, those magnetic fields extend out beyond the component. So relative to seeing if a material is going to be prohibited for air transit, we're going to go 4.5 meters around the circumference of that package, of that unit. And if we get a reading of 0.052 Gauss, then that is going to be forbidden from air transit. Still can ship by highway. Just realize that this is a limitation for air specifically. And always, regardless of whether we're talking about magnetized materials, lasers, batteries, chemicals, always consult the Department of Transportation, IMDG, and IATA regulations when shipping parts, materials, or waste, just to ensure that we have a proper hazard identification. And as a result, identify what are the proper preparation and shipment protocols to follow. And in this case, can you even ship it by that mode of transportation? All right, so just to wrap things up, we are here in the final stretch. So if you have any questions, feel free to use the chat or the question function. But just to take what Jake has shared with us and put it into some actionable items for you, what we recommend is that you identify parts and components that may have those magnetic fields. Or any other form of non-ionizing radiation. We focused our efforts in this conversation on those magnetic fields, but as Jake was mentioning, these magnetic fields are regulated under OSHA's non-ionizing radiation standard, which is also where we see other forms of non-ionizing radiation, such as microwaves, radio frequencies, and lasers being regulated. So identifying all of those parts and components that may have either those magnetic fields or other forms of non-ionizing radiation. And then by identifying those, then you can start those field assessments that Jake mentioned. Now, who on your teams might be valuable in that first bullet? So typically we're working with process engineers, or process improvement team members, those that are really familiar with the manufacturing process, really familiar with the parts and the material specifications for those parts. So we are typically, again, working with the engineers associated with that manufacturing process. And then once we identify the parts or components of concern, then we're able to conduct the appropriate field assessment based off of whatever type of concern that is, and then compare those to the appropriate exposure limits, whether it's ACGIH or other standard applications out there. And then once we know what types of results we are seeing, we can then tailor those programs, develop a program to implement the appropriate control measures for that hazard, maintain those controls, and then ensure the continued suitability of those controls. And then we just want to keep our program up to date because facilities change, process changes, new equipment comes, old equipment goes. And so we just want to make sure that whether it's through that management of change or other process that you have, that we're just keeping this up to date with those changing circumstances at the facilities. And just a little sneak peek, this is the last scheduled webinar for 2025. We've led 6 informative webinars over the year. All of those past webinars are available to you through recording. They're actually on the handout that my colleague Andrew was able to upload. So feel free to view any of those past webinars that we've had. And if there's any webinars you'd like to see us host in 2026, let us know. And here through the end of the year, we're going to be focusing on some of our in-person training. So, I mentioned very briefly waste and transportation relative to the topic today. If that's a topic of interest, whether it's hazardous waste or shipping of raw materials, we offer RCRA and DOT training. We'll offer a course in Farmington, Connecticut in October and a live course in our office in Greenville in December. We also have our online training that's available anytime. So with that, I will leave it on this slide here as we pause to see if anybody has any questions. So again, you can either enter a question through the chat function or through the Q&A function. I will highlight, for some reason, I was not able to upload the handouts in the chat, but my colleague Andrew uploaded the handouts. So everybody should have access to a PDF of the slides that Jake reviewed, as well as a supplemental handout. So Jake, you must have done an excellent job in talking about a complex hazard, as no questions or comments are coming through. So Jake, thank you for your time, and thank you for sharing with us your knowledge of this emerging hazard that we are seeing in some of our EV manufacturing space. And thank you to all of you for tuning into us today on this topic. And feel free to send us those recommendations for topics for next year in our webinar series. Thanks, everybody, and have a great rest of your day.